All right, so let's talk about dissolving some stuff in some other stuff. So we'll go ahead and start with gases dissolved in liquids. So an example of this would be carbonation. So like soda, for example. Um, this is carbonation, right? It's fizzy. It's because it's got CO2 gas inside of a liquid, which is the water, right? So you're pretty familiar with this in your life. And so if you think about gases, in general, gases don't experience intermolecular forces. So there's no kind of delta H of these solute-solute interactions. But the same rule still applies, like dissolves like. So for example, if you had O2 gas, right, oxygen gas, which one is it going to dissolve more in? Is it going to dissolve more in water? Or is it going to dissolve more in C6H14? Well, if you think about O2 as a gas, it's a linear molecule with both of them being oxygen. So overall, it's going to be nonpolar, right? And so is C6H6 nonpolar, while water is very polar. So if you think about where it's going to dissolve more, it's going to dissolve more in the C6H14. So still like dissolves like. But let's talk about some factors that affect solubility other than intermolecular forces. So, and again, we're talking about gases in liquids. So the first one is temperature. Right, so remember temperature is the amount of energy something has, and what's keeping the gas inside of the liquid is the intermolecular forces between the two. And so if you put more energy in, you're going to break those intermolecular forces, and so you're going to release more gas, and so solubility is going to go down. So as temperature increases for gases, the solubility decreases. And again, that's because you're breaking these intermolecular forces and causing more of it to go into the gas phase. So here's just an example of that. So on the left, they have cold soda, and you can see pouring it, there's barely any bubbles. That's because none of the gas is being released because it's cold and it's soluble. Whereas if you have warm soda or warm beer, you'll see a lot of fizz, a lot of head in the beer. And that's because all this gas is escaping the liquid because it's no longer soluble because it's too hot, right? And this graph on the right shows the same thing, right? Here's temperature in Celsius. Here's solubility. As temperature increases, solubility decreases. So as temperature goes up, solubility goes down. So let's take a look at that of an effect of this principle in our current day situation. So as we said, as temperature increases, and if we think about globally, we're thinking about global warming, right, due to human activity, right, we're pumping out a bunch of CO2 in the atmosphere, which is causing the globe to get warm. And that is definitely a fact. Anybody who tells you that is not a fact or that's not happening, they're either an idiot or they're lying. And so as the globe gets warmer, the bodies of warm water get warmer. And so when that happens, the solubility of O2 gas goes down. And so if you think about a fish, although a fish lives in water, it still breathes oxygen, the dissolved oxygen gas in the water. And so as the amount of oxygen goes down, the fish has no more air to breathe essentially, and so it dies. So we'll draw this little fish here, right? And we'll give a little tear. He's sad because he's dying. And so you can see examples of that in nature, right? You can eventually see these kind of mass die-offs of aquatic animals, and oftentimes that's due to a warming of the body of water, which causes a reduction in the amount of oxygen present, and thus suffocation for the little fishy guy. Continuing on, another factor that affects the solubility of gas in a liquid is partial pressure. So remember partial pressure from Chem 101 is the pressure from one type of gas in a mixture. So when talking about partial pressure, even though there's a bunch of different gases and there's an overall pressure of the mixture of the gases, all we really care about is the pressure coming from our gas of interest. So for example, so say we want to make some soda or some beer. So we want to dissolve some CO2 in here. Only the pressure of CO2 matters. Right? If we want to get more CO2 in that solution, we have to increase the partial pressure of carbon dioxide. If we increase the partial pressure of oxygen, nitrogen, argon, any other gas, it will not affect the CO2. Only the thing that's the same as it, right? And so in general, I kind of gave this one away. As pressure increases, as the partial pressure of a gas increases, gas solubility also increases. So here's a picture of an example of that. So here we have a can of soda, and when it's closed, right, we have a high pressure, right? There's CO2 gas in a little airspace in the can. It's under pressure. And then when you go ahead, open that up, the gas is under less pressure, right? There's less CO2 in the atmosphere than there is in the can, so the partial pressure decreases. And so the CO2 starts coming out of solution and then leaves the soda. And so your soda will become flat. So we're kind of talking about environmental effects. So here's a kind of a bit of a double whammy. So as humans put more CO2 in the air, more will dissolve in water. Right, as we're putting more CO2 in the air, we're increasing its partial pressure, thus we're increasing its solubility in water. And so this is a big issue because when carbon dioxide and water interact with one another, they form H2CO3. This is what's known as carbonic acid. And carbonic acid, as you may kind of realize, is an acid. So it will react to release some H plus and some bicarbonate. And so this H plus, this acid, is the part of the cause of acid rain, which helps kind of destroy our environment, destroy our things, right? It'll change the pH in water. And so it'll have a whole bunch of environmental effects, right? Certain animals can only live in a certain pH range. So overall, there's, kind of bad environmental effects. So you can see how the addition of CO2 into the atmosphere is a bit of a double whammy for the environment. If you read through your book also has an explanation of the bends. So it's when you go kind of scuba diving, the dangers of going up too high. We won't go over that in class, but if that's something that interests you, go ahead and check out your textbook.